Hey guys, this video is a tutorial on how to create this Nonagon mesh relaxation geometry using Kangaroo physics. If you like this tutorial, I request you to hit the like button and also subscribe to my channel for similar content. It helps me identify what's the kind of content that you would like me to cover next. And for those who would like to have access to the file, the prepared Grasshopper script, which would look something like this, properly annotated and grouped, you can access it from my Patreon channel. Link is in the description below. Now let's get started. In order to create this geometry, we'll first create a base surface B-rep geometry, which looks something like this. Then we will convert this B-rep into a mesh geometry and create custom subdivisions. This will form the base mesh on which we will apply Kangaroo goals and use the relaxation technique. The last step will convert the mesh into the final form. All right, so let's get started. We will be using the shaded mode, and to start off, we'll use the polygon tool. Take the center point, and you need to be clear about what you want to use this for. So some of you may want to use this geometry as a product. Some might want to use this as a large architectural structure. When I made this geometry, I intended this to be a temple structure, especially a Baha'i temple. A Baha'i temple has Nonagon symmetry, which is a 9-sided polygon, which is completely symmetrical. So the starting point for us in this case could be a Nonagon geometry or a multiple of 9. So I'm going to make a polygon with 18 sides, and I'm going to keep the outer diameter as, or the outer radius as 30 units or 30 meters. Okay. Now, if I go back to the geometry, I've got the outer circle. Then I need a polygon to define the base of this geometry. So we take the center point with 18 sides still intact. Oops. Yeah. Let's create another polygon. And this time the dimension for this one could be 16. All right. And then we need another one which could be at 12. Now this can vary as per your liking. At the moment I'm using these dimensions. That's completely up to you. So this can be 14, 18, 20, whatever. And then we need another circle or a polygon for the top. So I'm going to use a 9-sided polygon this time, and the radius would be 4, right? So once we have these 4 polygons, let's set them to their heights. So I'm going to have an entry height of 6 meters. When I say entry height, I mean this height over here. So I'm going to talk about this height from the base till the top, 6. And that's again subject to what you'd like to make. And the top, let's put it at 24. All right. Now, once we have this, let's create our surface. I think it would be better if I take the top view. And looking at the top view, there seems to be something a bit off. Oh, well, not really. Okay. We create this surface, which is over here. And then we create this surface, followed by this surface and this surface, right? Once we have these 4 surfaces, we need to join them using the join command. and ensure it's joined. Once this is joined, we can use the array polar command, which asks us which object to select, which is this one. Press enter. Then you've got the center of the polar array. You take the center point over here. Number of items would be 9 because you want to repeat it 9 times. That's fine. And the angle to fill is 360. So that's 360 over here. That's also fine. Enter and enter. So we get this as our base geometry. Now, once we have this, let's take a fresh Grasshopper script to start with. And what I'm going to do is just switch this off. Okay, let's take a fresh Grasshopper canvas. We are going to use the brep command and set multiple breps. Right? Just check this. We've got 9 reference breps. That's fine. Once we have this, we can hide the base geometry. We don't really need to see it, which is the Rhino geometry. Okay. Now the first step is to convert this brep into a mesh. Now the simplest way of converting a brep into mesh, which will retain the base geometries. That means if you have a quad over here, it will convert this quad into a quad mesh without really further subdividing it. So this can be done using simple mesh. Now simple mesh component can be found under mesh, utilities, and over here, simple mesh, right? Now, the use of simple mesh and the use of other mesh brep components has been covered in some of my earlier videos. Link for those videos are in the description below. So once we have this mesh, we need to check once again, and over here it says 9 mesh. Because we had 9 different breps, it's converted into 9 mesh. Once we get this, you would notice that for each mesh, you've got 16 vertices and 4 faces. That means you've got additional vertices in these meshes. So one of the first things we need to do is join the mesh. So we can go to Weaverbird's join mesh and weld component. For this particular exercise, you would need Weaverbird component or the Weaverbird plugin. So you put the mesh in. Here you see the option for welding. So it's false by default. So you need to set this to true. So we'll go to Boolean set true. Once we do this, we see that our mesh input has 9 values, whereas the output has 1 value, which is the weld mesh. Now, once we have this, we just want to ensure that there aren't any additional vertices. So let me just do a mesh weld vertices again over here. And yeah, just to ensure. So what you can see is that we had 56 vertices earlier. After using the weld vertices, it's reduced to 54. So there's been some amount of optimization. Now, once we do this, the next step is to divide this mesh into smaller segments. We can do that using Weaverbird's constant quad split subdivision. So you take this, here's the mesh. Now, this component does not allow you a subdivision which is more than level 3. So we use 3 as the maximum. Now, once we do this, and let me just hide everything else before this, you'd notice that the corners starts rounding up, right? Like over here and over here as well. This is something we want eventually, but not right now. So you need to look at the smooth naked edges and see the inputs. Over here, the default input is 1. That means the naked edges will tend towards a spline. Now, for now, we need to keep it at fixed so that naked edges will not move or be modified. So we change it to fixed, and that's how we want it. If you'd like to increase the number of subdivision, you can see that as soon as I make it 4, it just does not subdivide it any further. So another way to do this is to just copy and paste it again. and remove the subdivision. So you got level 1 subdivision, and now you have something which is a bit more fine than the previous one. Okay, so this will act as our base mesh. So let me just take this as a mesh input. Oops. Here, right? So that's step number 1. We take the B-rep, convert it into simple mesh, join it, weld it to ensure we don't have additional vertices, and then subdivide it to get the final mesh. The next step would be to take this mesh and apply certain goals, Kangaroo goals. To get started with this, let's analyze what kind of goals we need to create. Okay, now when I see this, let me just switch this on. Yeah. Now when I see this, one of the immediate goals that I recognize is that all these edges, which are straight at the moment, needs to curve or needs to follow a circular pattern, right? So we need some anchor points over here, which will anchor all these individual naked vertices to a circular arc. The same thing needs to happen for the top profile as well. So we need these profiles to anchor to a circular form. Same needs to happen to these triangular base as well, right? To do this, let's identify all the naked vertices. To identify the naked vertices, let's use a naked vertices component, which can be found under Kangaroo's mesh. Is it mesh? Yeah, naked vertices. We give the mesh as an input and take the point. Now, once we take the point, it's important for us to see that only the base triangles and the edge of the polygons are highlighted as naked vertices. In case you see any additional vertices, let's say something like this being highlighted as naked vertex, that means there is some issue. You need to go back to your welding and check whether your mesh has been welded properly or not. So here's the output to naked vertices. Now, one of the things that we can do is to group them into individual branches. And this grouping will happen based on their proximity. So let's use something called point groups. And let's set a distance. And this distance is going to be dependent on the size of your geometry. So over here, I can easily imagine the distance between them is less than 1 unit. So let me just set this as the distance. Now what this will do is that it will create 11 different groups of different number of points. Now let's try to understand this. So you need to have, hold on. Yeah. You need to have 1, 2, 3, 4, 5, 6, 7, 8, 9 for these, then 10th for this one, and 11. So you need to have 11 groups, and that's what we get over here. Now using these point groups, and let me just simplify this to get rid of additional branches. Great. Once we have this, we want to find the center point for each of these groups, and then use the center point to find a circular radius that would be ideal for each group, right? So let's find the center point first. So to find the center point, we can use the component called average. Now average will take the input or the location of each of these points and get an average point for us. So here's the average. So we have an average for all the triangles, we have an average for the bigger polygon, and then we have an average for the smaller polygon. But each of these polygons will have their own radius or a different radius to comply with. So to find that radius, what we'll do is we'll take this point and we'll take these group of points, and we'll try to find the distance between the center point and all the points. So we use the distance component here. So what we get is a list of distance, and the distances are such where we get all these distances in one group, right? And what we'll do after getting these distances is take the maximum distance, which visually looks as this one. Whichever is the maximum, we'll use that as a radius and draw a circle. So we do this for each of the 11 groups that we have. So we have the distance and we got different distance values. Now to find the largest distance value, we'll just use the sort list component. Sort list will help us sort these values in an ascending order. So if I were to pull up a panel, if these distances are listed in this manner, sorting will give you the distances from the lowest to the highest. Now for each branch, we would want to highlight or extract the largest value, which is this one. So one of the easiest ways to do that is to just do list item, take the keys and use an index of -1. -1 will take the last index of each branch. Just to check again, so we get the highest number for each branch. We can use this as radius for the circle. So let me use a circle command. So the plane or the center of the circle would be this arithmetic mean, which is the center point, and the radius would be from the list item. So you get a radius. Let's just check it with the point groups. So yes, we got one radius for each point group. If this is clear, let's move on to the next step, which is to find points on the circle that will correlate with these points, right? To do that, let's get the number of points that we have in each of these lists. So to get the number of points, let's use list length. So it tells us that branch number 1 has 48 points, branch number 2 has 288 points, that's the bigger circle, and branch number 3 has 48 points, and so on. We'll use this information to subdivide the circle. So we do a divide curve and we do a count. So we've divided the circles into their respective number of counts over here. Once we do that, let's try and relate our mesh vertices or the naked mesh vertices, which are over here. Let me take them into a separate point container, right? And let's try to draw a line between our divided points and the original points. Ideally, what we would want is that these mesh points should go and anchor to their closest curve point, right? Whereas currently these points are unorganized. Hence, a point which is over here is trying to anchor to a point which is on the other side, which is not ideal. So one of the things that we can do is to take these points and sort along curve. So here are the points and here's the curve. After sorting, let's check this once again. And now the points are connecting with their closest curve points. So we can get rid of this line and we can use an anchor goal. We go to Kangaroo, points, anchor, and we use these sorted points as the points that we want to anchor, and the divide curve points as the target points where we want these points to go and anchor to. So that's our first Kangaroo goal. Let's do a quick recap. We took the mesh, we took the naked vertices, which are these. We divided them into groups based on distance. Then we found the center point. We found the largest distance for each group and used it for the circle radius. Then we divided the circle into a number of segments based on the number of points correlating to each group. We also sorted our naked vertices along circles just representing each group, and then we anchored them, right? So that's our first goal. The other two goals are simple. We need to use the show component. The show component helps us visualize the mesh output. So that's show. Let's bring it all the way to the front. And let's also use mesh, or let's just go to goal mesh and use edge lengths. So here's the mesh. Here's the length factor. Let's use the length factor as 0.1. Now, if you want to know how does edge length component work, or how does this goal work, or how does this goal work, I've made individual videos which are listed in the YouTube channel. Just go to Strip Morphologies playlist and you will find relevant videos on that. Coming back to this, we've got show, edge length, and anchor. Let's use a goal or a solver. So we go to Kangaroo solver. We need goal objects. The best way to do this is to just use a merge component. Ensure that your show goal is the first one that goes into the merge component, that is its data 1. Then you get edge lengths, and then you get anchor. Flatten the list. This goes into result. Then you need a button over here. It's wise to just lock it, and you get a Boolean toggle. Once you have this, you would also want a list item. And a mesh output. Now, once you have this, you can just switch it on, retoggle or reset, and there you have it. Geometry, a Nonagon relaxed mesh geometry, right? And if you'd like to express this mesh into individual strips, you may do that by first taking the mesh. Ensure that your solver is converged. If this is running, wait for it to converge, or set this to false so that your solver can be paused and you can take the final output and proceed with it. So you take the mesh and you can use the stripper component, right? Here's the mesh stripper component, and what this does is that if you use a list item and you use, let's say, a number between 0 to 100, it will break this geometry down into strips. So once you have the mesh strips, you can use mesh edges. To just visualize the edges separately, take them as lines, and you apply custom preview line weights. Now this component is part of the Human plugin. So to access custom preview line weights, you need to download Human, which looks something like this. So under display, you get custom preview line weights. Here's the geometry. Here's this shader. We'll set this to black for now. Right, now when you notice over here, you have strips in two different directions. You've got a pair of strips which are going in vertical direction. Here you've got strips in the horizontal direction. To fix this, we can go to Kangaroo, go to mesh. You have something called the mesh direction. Using this will unify the direction of all the mesh faces, and then you get all the meshes or the strips in one direction, right? If you'd like to flip the direction of the stripping, you may just use the mesh turn right after mesh direction, and this will give you the mesh strips in the opposite direction, right? For now, I'm just going to keep it this direction, and the last step would be to use something to visualize it. I'm just going to use custom preview. Custom preview is a default Grasshopper component, so put this into the geometry, use a swatch. Over here, disable preview for the entire script, and turn on the rendered preview. That's what you have. Let me just make some slight tweaks, which is use the custom preview. Okay, so there was a mistake because I was using mesh direction. Now it's fine. So that's your final output. You get a mesh geometry like this. If you like this tutorial, please hit the like button and subscribe to my channel for more weekly content ahead. Thank you.